This week, we're going to start specifically on bash. So the things we're going to do really are very directly applicable to bash and only peripherally applicable to other shells. So bash has been around for a very long time. It's not the original shell from Unix, but it is one that was created shortly after the Linux work got going. As a matter of fact, they were developed around the same time frame. Linux itself is actually a derivative of Unix. It's based on all the Unix philosophies. It's implemented along a very similar pattern and path as the Unix operating systems. And in particular, it incorporates, or has in the past, incorporated a core philosophy of the Unix world. And that is that when we create software tools, those tools should do clearly defined tasks, should do those tasks well, and should not attempt to do other tasks they weren't specifically designed to do. So if we think about a program like Outlook, for example, Outlook would not be in compliance with this philosophy because Outlook is one of those programs that's a bit of a monster. It does 500 different things, and various people would have their arguments about what it does well or what it doesn't do well. But Outlook generally does not play very well with other programs. It saves its data in formats only it can read. Even it can't always read its own files, and you have to kind of restart it when you try to transfer things from one place to another for certain portions of the data. And it tries to kind of be a solution that solves all problems for all people kind of thing. As a result, most of the time you find when people use a program like that, they only use certain parts of it, just the ones they have learned, usually through trial and error, how to make do what they need done, and they don't really go any further because there's too much there. Okay, so the Unix philosophy is kind of the opposite direction. It says, oh, if I need to make a listing of my files, I should run a program that lists files. It always works. It always works the same way. It's very straightforward, and I can give it input from another program or send its output to another program without worrying about whether they can talk to each other. If I want a program that searches text, it should be able to take text that comes from any program and do the same kind of search and work the same way every time. The idea is that we create lots of smaller tools and we make them work together. We make them interoperate. Bash is a shell. Bash is a program that allows us to give commands to tell the operating system which of these tools to run, how to hook them together, and what to do with their input and output. So it basically is our interface to allow us primarily to start other programs. In other words, bash is not a goal. It's a method to achieve a goal. It was produced back in the 1980s. It implemented the design philosophies and command structures of the existing shells at the time, which themselves had been around for some time. They tend to be linear. So we do one thing, then we do the next thing, then we do the next thing. We can start something running and disconnect from it and go do something else, but the shell itself is only doing one thing at a time. Bash is an open source program. You can get the full source code for it. It is very actively maintained. It's an absolutely core part of the system. And many of the tools in the operating system are actually scripts written for the bash shell or other shells that are in the system. So it is a critical core piece of the system. It's designed to do one thing and to do it well and to work well with other programs of that nature. When we say execution is linear, we do things one step at a time. That sometimes is also known as structured execution. It can be a little bit of a misnomer, but anyway. Another core thing to know about it, all data is treated as streams of text. That doesn't mean you can't have binary data. It just means most of the tools you're going to work with on the command line are able to take text input and produce text output. And you may well have to do conversions on things if you want to produce binary or consume binary in programs that are generally designed to work with text. When we create a script, all we're doing is taking those commands that we would type on the command line with our keyboard and putting them in a file. We talked about that last week a bit. When we save commands in a file, we are creating scripts. There are lots and lots of different kinds of scripts. A bash script is one that we run in the bash program. So the commands in that file have to be bash commands, or commands that work in the bash shell, support the syntax of the bash shell, and abide by the rules of the bash shell. Mac OS is Unix, not a derived from Unix. It is Unix. It is an official Unix variant. It has bash. The Mac OS bash is very much the same bash that's in Linux. However, a lot of the commands in the system, because it is Unix, are not quite the same as the commands that are in Linux. Unix has its own set of utilities and tools. Linux also has an extremely similar set of tools, but from a different source, from the GNU program. As a result, even though the same commands will appear in both operating systems, some of the options for those commands may be different. So when you write scripts for bash for Mac OS, unless you've specifically taken that into account, you will find that those scripts are often not portable to Linux and vice versa. And it's because of differences in the rest of the system, not so much in bash itself. So that's a quick overview of what bash scripting is about specifically, and some core philosophy or concept items to keep in mind no matter what you're doing with bash scripting. So we have some basic topics we're going to cover today, and then we're going to cover a few things that are a little more advanced. Let's get through the basics first so that everybody kind of has a ground rule to start from. Let's talk about how we create and execute our scripts, what we can actually put into them, and where we should be keeping them. Those are kind of common concepts no matter what we're doing with our scripts. So we've already said putting our commands in a file makes a script, but the type of file is important. They need to be plain text files, not WordPad RTF documents, not Word documents, certainly, not any kind of a formatted text type file, plain text only. Okay. We can create them and edit them with any program that can create or edit a plain text file. It doesn't have to be a special program. We can use Nano. We can use VI or Vim. We can use a program like CAT with output redirection and input redirection to take our text and stuff it in a file. We can do anything that creates a plain text file. And as long as the data we're putting in the file is bash commands, we have made a script. If you're doing things that are quick and dirty, small tasks, people typically will just use a simple text editor like Nano or VI, whatever your preference is, or other ones. If you're using a graphical interface and you have a tool like Atom available, that can be very, very helpful because it provides additional assistance by recognizing a script file and providing error highlighting and syntax highlighting. That's not required to write a script. It simply makes it a little easier. When we create these text files, we have to think a little bit about the name that we're going to use for them. The Linux operating system does not care what the name is. You can put any extension on it you like. You can have no extension on it. As a matter of fact, quite a few of the system utility programs that are actually shell scripts don't have any extension on their name. So the operating system itself doesn't care. It actually looks inside the file to figure out what kind of file it is. Programs like Atom, like Visual Studio Code, and various other graphical tools quite often don't follow the same rules as the operating system. Many of those only look at a file name and depend on that name being correct and accurate and having a file extension that is recognized in order to properly manage the file or handle the file. So for that reason, certainly in this course, and perhaps even beyond it, you may choose to always put .sh on the end of your file names. So the sh file extension is recognized by tools like Atom to say, this file is expected to hold a script, and you should open it as a script. Now, it's not .bash, it's just .sh. And the reason is you may have any of a number of different command line shells. And again, you would only really normally have .sh as the extension, no matter which shell it is. Z shell, C shell, bash, Bourne shell, doesn't matter. .sh. Okay? If you don't name it that way, the GUI tools often will not provide you any assistance in editing the file. They won't recognize that it's a script file. Not necessarily harmful, but it kind of gets rid of the point of using a GUI. Okay. Quick reminder on the last bullet point on this slide, do not use a word processing program to create or maintain script files. They will add formatting data. They'll basically turn it into a binary file. Do not use them for this. Once we've created a script file, the next thing we have to care about is being able to run that script. Now, we actually did this at the end of our class last week, so we've actually seen how to do this already, but there is more than one way. Generally speaking, there are two ways to execute a script. The first and most common way is to simply enter the file name of the script file. It gets treated as a command if the file is executable and the shell can find the file based on the name you gave it. The second way that is less common, but is often done when troubleshooting, is to run bash itself and put the file name after the bash command on the command line. So we first thing we need to do is go ahead and make our script file. In the example on this slide, the cat command sends its output to scriptfile.sh and gets its input from the command line until it sees EOF by itself. And there's two lines there. They look quite similar to our Hello World script from last week. And those lines get put in the file. Without doing anything else, we could execute that script file by using the second example, bash space, the name of the script file. It will start a bash process. That process will get its input from the file, run the commands found in the file, and when it gets to the end of the file, that bash process will exit. That's useful if you're not wanting to make the file executable yet and you don't want to put it somewhere anybody might find it or run it by mistake. You can very intentionally run it that way. Once a script is running and doing what you want it to do and you expect to use it more than once, you'll want to actually simply type the file name as a command rather than typing bash in front of it. To do that, it needs to be executable, as we mentioned. The change mode, chmod command, is used to change file permissions on the command line. Anything that will add your execute permission bit so that you can execute it is useful. If you own the file, it's your file, you might want to limit it to only you being able to execute it. So that would be u plus x. That's one of the ways to specify it, saying the user can execute this. If you want everybody to execute it, you would just use plus x. There's various options for that. And then, of course, give the file name. You can then run it as a command by entering the file name. If you enter only the name of the file, unless you happen to have created it in a directory that bash already knows to look in for commands, it will come back and tell you file not found. The reason is bash, like all shells, has a path parameter. It's actually stored in a variable called path. And in that variable is a list of directories where bash looks for the commands you typed. We said a few minutes ago that one of the main things we do with bash is run commands. We run utilities found in the system, programs and tools. How does it find them when we type the command? Well, when we type a command like ls, for example, it opens up its path variable, takes the first directory stored in there, and looks in there for a file called ls that is executable. If it finds it, it runs it. If it doesn't, it goes back to the path variable to get the next directory to look in, and so on. And it does this until it gets to the end of the list. If it gets to the end of the list of directories in the path variable and hasn't found a file that is executable and has the same name as the command you typed, you'll get the error, command not found, because it literally just went looking for it. The way to avoid using the path variable is to actually put the path on the command line. So in the third example, right underneath the change mode command on this slide, where it says /script file, that's telling bash, don't use the path here. I'm telling you where to look. Look in dot, which is the current directory. /scriptfile.sh means run the file called scriptfile.sh from the current directory. Now, if we always had to put in the path to find our commands, that would certainly be a nuisance. So the other way to do this is put your script file in some directory that is in the path variable, or modify the path variable to include the directory where you store your script files. You could move the script file to an appropriate directory and just run it as a command, and it will actually find it. Or you could modify your path to include it. And again, just enter the file name and it will now find it because it's on the path. In terms of testing scripts, one of the other things that is commonly done is that the scripts themselves simply contain commands. They're the same commands you would run on a command line. So you could actually copy and paste the lines from a script file, open in, say, a second window, and paste them right onto the command line to run them to see what they do. That actually is essentially the same thing as running the script file. It's normally only used for testing purposes, though. So we know how to create the file. We know how to make it executable. We know how to tell bash how to find the file to run it. Now we need to talk a little bit about what we would actually put in the file. We've said that it's commands, but there's actually a little bit more than that that you might find in a script file. Scripts can contain those commands. And as a matter of fact, if a script doesn't have at least one command in it, it's technically not a script, it's just a text file. Script files can contain blank lines. They're used for readability purposes to visually separate parts of the script so that they're easy to spot for a person looking at the script. We can have comments, which are a form of documentation in the script. And we can have inline data, literal text data in the script to be used by the commands in the script. The script needs to have at least one command in it. And there are no practical limits on how long your script can be. You can have a script that's 5 lines long, 1 line long, 10,000 lines long. If you were in my second semester Linux network admin course, or in a course that somebody taught using my materials, you used a script called the server check script to verify your lab activity progress and to make sure things were working the way you expected and kind of get your marks figured out for it. That shell script is a script that I wrote and I keep maintained. I revisit it every semester and update it. That particular script, I don't recall the exact number, it's about 800, 900 lines long. So scripts can get to be a fair length and still do useful work. The commands in your script are exactly the same ones you would use on the command line. You don't write them differently in the file than what you write them on the command line. The nice thing is that means you can test any command right on the command line before you ever put it into a script. If a script is misbehaving, you can type the commands from it right on the command line to see what they do and what happens and find problems. Scripts normally start executing at the first command found in the file. They execute them in the order they appear in the file, until they get to the end of the file. If a script essentially runs out of commands, it goes off the end of the file. That is what's called running out of commands. That is a normal exit for a script. And when a script ends by running out of commands like that, no matter what happened when the script ran, it is considered to have run successfully because it reached the end. Now, there's two cases where a script may not reach the end. One, you may have built some intelligence into your script to test something, decided that the test produced or identified a condition whereby the script cannot continue, and you would use an exit command to make the shell script end early, okay? In which case it doesn't run all of the commands. It exits when it hits the exit. There is a third way that a script can end, and this one is unintentional, pretty much always, and that is when it runs into what's called a fatal bash error. So a fatal bash error is not something like a syntax error unless the syntax error is a bad enough one that bash can't figure out what the next command in the script would be. So an issue with quoting, for example, where it looks like the rest of your script is just text that isn't even a command. That would be a fatal bash error. The other fatal bash error you may encounter, bash, like all shells, can do some arithmetic, can do some math. Dividing by 0 is a fatal bash error. You can't divide by 0 in the shell. If you do, bash will exit with an error. Generally speaking, our scripts will end because we've put in an exit command and the correct conditions have been met, or they simply run out of commands. They run the entire script and finish. Both of the scripts on this slide do the same thing. They both have the same first line, hash bang bin bash, which we have at the start of all of our scripts. Then they have a second line, which happens to be a comment. Then there's a blank line. This is for readability, so that we can clearly see, well, the stuff at the top is information about the script. The stuff at the bottom is the commands. Then in the first one, there are 2 echo commands that use some literal text, some inline data, hello world, and I am process number $, to produce output with the echo command. The second version of the script there, the one called hello world templated.sh, doesn't use echo, but it has the exact same literal data. Instead, it uses a cat command with an input redirect, the double less than symbol EOF, to say get the input text from the command line until you see the EOF. So it reads in hello world and prints it out. Reads in I am process number $, and prints it out. And then it sees the EOF and finishes the cat command. So both of these scripts do exactly the same work, even though they've used slightly different commands. Scripts themselves are generally free form. You can put in any commands you want, in any order you want, to achieve whatever task you wish to achieve. The only exception to that rule is the very first line of your script. The very first line of your script is a very specific line. It's known as the command interpreter specification. We've been using #bang/bin/bash to say this is a bash script. Well, what that line really is saying, the #bang is what tells the operating system, this is a script of some kind. And the rest of the line is actually the full command to run to actually feed the rest of the script into as a command, as input. So when we put #bang/bin/bash, we're telling the operating system, run the bash file found in /bin, which is our bash shell, and give it the rest of this file as input. There's different ways to specify this. You can use different programs. If you have multiple versions of bash on your system because you're developing for bash, you might need a more sophisticated line like #bang user bin env space bash to say whichever bash my environment has chosen. You might want to supply options to the command. For example, if you want your script to always run in debug mode to print out what it's going to do before it does it, you would need to run your bash with the -x option. So your first line might read #bang/bin/bash space -x means run the bash script in debug mode. At this point, you should be kind of figuring out, after the #bang, we can put any command that makes a script run. If the command is bash, it's a bash script. If the command is something else, the script is also something else. If I put the path to the Z shell there, the rest of the script would need to be Z shell commands. If I put the path to my Perl interpreter for the Perl programming language, then all of the commands in the file need to be Perl commands, and so on. So this first line is very important to the operating system. That #bang line, you'll notice, starts with the hash mark, with the number sign. The number sign actually serves two purposes. When it's with the #bang, it's telling the operating system this is some kind of script. If it is not the first line, or if it's not the operating system running the file, then the hash mark just means the stuff on this line is a comment. It's documentation. So any line that starts with that hash mark is ignored by the interpreter program. So when we put a line in there, hash mark space, this is a comment, when bash is running this file, it just ignores this whole line. It doesn't care what's on it. You could put 14 bash commands on that line and it doesn't care. The hash mark tells bash, ignore this line. Okay? Comments are for the person who is using the script, and in particular, the person who's either writing it or maintaining it. They will typically explain what the script is for, what it's supposed to do, information about the data it uses, maybe things that are not obvious about it. It's documentation. The reason being, when we write a script, often we're creating a tool for ourselves or someone else. And once we've got it debugged and working properly, chances are we won't look in that script file again for a long time, if ever. At some point, things may change in our system that cause the script to require an update, a change. If it's been a long time, you may open up your script file and say, wow, I have no memory of writing this. I can't remember what I did with this. And you could wind up in the position of the unfortunate fellow in the meme. Some interpreter programs allow you to start comments in the middle of a line. So the third example on this slide that says echo hello world hash mark, this is a comment on the same line. If that was all one line, some shells will let you do that, some shells will not. Generally speaking, put your comments on separate lines from your commands, then you don't have to remember which ones do what. Comments are a form of documentation. It's not uncommon, if this is a tool that's going to be in use for some time, to put some helpful comments at the start of the file saying, what the name of the file is supposed to be, perhaps who wrote it, when they wrote it, what it's for, what it's supposed to do, and perhaps even describe its input and output if that is not obvious. You may also use comments to separate sections of your script. And you may use comments to explain or document specific commands that are hard to read or work with. So in the example on this slide, we have a script that does exactly the same thing as the first two scripts we already looked at. This script prints out hello world and then says, I am process number and its process ID. Just like the first one with the two echo commands or the second one with the cat command. Why would the script look this bad? Well, if we take a look at the comments, we can get some information about this script. We can see it's called Hello World Ugly, and it's an exercise in obfuscation. So obfuscation means we have done this in a way designed to hide what it does. We're trying to make it hard to read. We don't want someone to easily see what's going on. I used to run all kinds of obfuscation contests. So this might have been an entry in that. As it happens, it wasn't. I wrote it specifically for this slide. It then describes what the script does. It displays hello world and then displays the process ID. The next comment we have is after a blank space. So in other words, we can visually see the description of the script is separate from the next part. And we can see in that comment, the next part, it has function definitions, and then there's a command to define a function. And again, we have some blank space, so we can clearly see where the function definition part of our script begins and finishes, just visually. It's very easy to see. Then we have a comment that says we're starting the main script body. In other words, the place where the commands are that do the work of the script. And then because the next command that's there, and there's actually two of them, are really hard to read. It says this is a silly way of creating the output text. We start with similar text, stream edit it in a pipeline, and it's a trivial form of code obfuscation. So we know why it was done. We know generally what it's doing, and if we want to know the down and dirty details, we actually need to look at the commands and see what they do. So comments. Checking the chat here to make sure there's no questions. Samuel, yes, the number sign is, the hash mark is used to start a comment. Yes, when it's with the hash and the exclamation mark and the very first line of a script, it's used to indicate the command interpreter. Right. So what I'd like to do then is get you started on the lab to create your first scripts. Technically, we created our first one last week with Hello World, but you're going to be modifying that